Okay, so hi everyone. Welcome to our second talk of the series in fall semester. So again, in case there are some new audience here, this talk series will be given by the awardees of NCU-Delta Young Astronomer Lectureship, which was founded by the National Central University and the Delta Electronics Foundation to recognize young scholars who have made outstanding contributions in this field. So each year, the awardee will be invited to Taiwan to interact with the local astronomers and the public. So the first award was given in 2012, and the original plan for this year was to invite all the previous awardees to come back to Taiwan. But unfortunately, we have to make this event online due to the pandemic. So our speaker today is Professor Liu Jifeng from NAOC. So it's our great pleasure to have him here. So I think Professor Liu received this award in 2016, and he's now the Deputy Director of NAOC. And I think he's a world expert in using multi-wavelength facilities to study the stars and compact objects. So for example, he has made great contributions in black hole observations, such as measuring the black hole mass in ultraluminous X-ray source. So today he's going to share with us a very exciting and ambitious project called Sitian, so which in Chinese, I think it means sky monitoring. And so just a few announcements before we start. Please mute yourself during the talk. And if you have any questions or comments, you can leave them in the chat box anytime you want. We will come back to those questions in the middle of the talk or during the Q&A session after the talk. All right, Jifeng, I will let you take this away if you are ready.
Yep. Thank you, Professor Pan. I'll start my talk. Sitian Project for the Transient Universe. Of course, this talk is on behalf of our whole Sitian consortium. So the universe, if we look at the universe in a static way, you know, you see our Earth, you see our sun, you see all the stars, you know, and the Milky Way, and a lot of Milky Way-like, you know, spark galaxies and elliptical galaxies, and then you see the, you know, the whole structure of the universe. I mean, in some sense, it's a hierarchical structured universe. But then, on the other hand, you know, the universe is transient in nature because every, you know, heavenly body, you know, every star actually is ever changing. It's not like in Chinese, you call it a hengxing, but it's not constant star. It's ever changing star, right? So it's transient in nature, not only stars, but a lot of other objects. I mean, if you look at the picture, you know, to the right, we actually, you know, here we actually, you know, list, okay, I'll just move this, okay. It's blocking my vision. Okay, so if you look at the figure to the right, you see a lot of variable objects like a supernova, you know, all kinds of supernova, and like kilonova, you know, from the merging of neutron stars. And then, you know, you have gamma ray burst, afterglows, you know, a lot of things. Well, I mean, when we talk about transients, you know, we talk about the duration of the transients, you know, the time scale. It's a characteristic time scale. I mean, here you can see, you know, the characteristic time scale actually ranging from, say, you know, the right actually is years to months to days, and then to, you know, a tenth of days or even to, you know, minutes or seconds. But then what's our capability now? I mean, you see this, you know, vertical bar, you know, to the left actually is less than a day. It's a rarely explored space. To the right, you know, above a day, the time scale is well explored. But then, you know, for example, the supernova, it's well explored, but the early stages are not well explored. So, well, I mean, you know, all these studies, you know, we have learned a lot. For example, you know, the the EM counterpart for gravitational wave events. I mean, here shows the example for GW170819. It's LIGO and Virgo actually detect the merging events. Soon on you have a gamma ray and X-ray detection, and then later on, actually it's 11 hours later, the SWOPE telescope, 1 meter telescope, actually identified the optical counterpart. And then after another half a day, we actually obtain this optical spectra of this one. If you look at the light curve, from all wavelengths, and you actually see this, rising and declining shape, it's actually consistent with the kilonova model. This model depicts like two neutron stars collision, into each other, and then the materials get split out, and then because of the great energy it contains, it actually very soon it becomes a fireball, just expanding. And basically what we observed for this event, actually this is this fireball. And of course you actually see these absorption lines, and you say, okay, that actually means high opacity, and that's evidence for lanthanides, this heavy metals. So when this event happened, people actually you see in the news, gold actually produced from neutron star merging. They are actually based on this observation, saying it has heavy elements in this explosion. But then, to tell the truth, this is actually a feat for transient study. You actually catch this optical counterpart only half a day later, right? But it's also a pity, because now we actually don't have the power to discriminate between different equational state models. That's actually very crucial, very useful, significant. I mean, if you look at a figure to the lower right, you actually see the red curve and the blue curve. The red curve is the usual neutron star equational state model. The blue curve is another kind of exotic, but some theorists actually say they have value in it. And in this case, the blue curve actually seems like it fits the observations better in the late on stage. But the biggest difference between these two models actually lies in the first 5 hours of this collision. But of course, I mean, current time domain machines actually didn't have the capability to catch this 5-hour early light curve. Another example I want to mention actually is the supernova cosmology. The type 1A supernova, we know they are standardized candles to measure the distance. If you look at the light curves of different 1As, they're very different. But if you apply this stretch factor, you find that the scatter of the peak luminosity actually is rather small. So that's why it can be used as a standardized candle to measure the distance. So people actually use 1A as this to measure the expansion of the universe. This Ricino, they actually did it like more than 20 years ago. So what they found actually is the supernova actually dimmer than is in a universe of pure matter. So the acceleration, the expansion is accelerated. So that means it has something weird. What now we know is called we call it dark energy. So of course they won the Nobel Prize, but then if you look at the data sets, it has a lot of are large uncertainties. I mean, the reason for that is 1A, supernova 1A is a candle. Actually, is a heterogeneous class. Its progenitor could be a single degenerate model or double degenerate model. A single degenerate model means you have a white dwarf, but then you have a companion star. Either it's a red giant here, like I show, one solar mass red giant, or main sequence star, large mass, 6 solar mass, or a smaller 2 solar mass main sequence star. That's single degenerate scenarios. Then it can be a double degenerate, 2 white dwarfs, they just spar in and collide into each other and explode as 1A. Of course, I mean, different mechanisms, their light curves are bound to be very different. But here, I mean, in their work, they didn't differentiate between different models. That could be the reason why it's scattered a lot. One way out actually is you actually examine the early light curve of these 1As and try to tell whether they single degenerate or double degenerate. And then you use 1As from similar progenitor, and then of course you will have a smaller uncertainty, right? So basically what we see actually is the time domain astronomy has achieved a lot, but then there's still some pities because it cannot go into very short time scale transients, not to say and it cannot catch the very early light curves for explosive events. So basically we need to do better with this sky surveys. Here I list the current and the planned sky surveys. Some sky surveys like ASASI, All Sky Automated Survey for Supernova, and like GWARC, ground-based wide-angle camera, they are rather small aperture and a very shallow detection limit. So we're not talking about those. We're talking about the surveys with large telescope and the very deep detection limit. Well, I mean, here I list like Sitian is our project. Try to we're pushing it to say 2025 or maybe later. And then RSST, it has been for a while, for like 22 decades, and it's going to be commissioned very soon. And then this Mephisto, it's a 1.6 meter in the skies with 3 color cameras. It's going to be next year or year after. And then we know Pan-STAR, it's a decade ago at Hawaii, and then Sky Mapper in Australia, it has been there for a while. And then that's a WFST is a 2.5 meter telescope to be installed at a Lenghu site and next year or later. And then that's the Zuki Transient Factory. If you look at this table, you notice that their aperture, of course, is larger than 1 meter, and most of them are just one telescope. The detection limit ranging from say below 20 magnitude to 25 magnitude per exposure, and it's a field of view ranging from 1 degree to say a stunting 47 square degree for ZTF, and most of it try to cover the whole sky. When we say whole sky, that means for one night it's just well, the whole night for a telescope is 10,000 square degree, but then because the Earth is rotating, so mostly it's something like it can be double, like 20,000 square degree. And then the cadence is the key, and for the for the early stages of explosive events or short events. Here you can see, except for Sitian, most of them, the cadence actually longer than 2 days, right? And these, of course, are not good for faster transients or early light curves, within days, for these explosive events. Well, I mean, here I show two, time domain state-of-the-art facilities. One is Zwicky Transient Factory, is a 1.2 meter aperture, modified Schmidt. FOV is 47 square degree. It's kind of striking, and the renovation, the renovation cost like $30 million. That's approximately 200 million renminbi yuan. And this actually is, it is the time domain machine for now. It actually in operation, it discovers hundreds of thousands of transients every night. It's not discovering too few, it's discovering too many. So, I mean, because when you are given hundreds of thousands of transients, I mean, you just don't know what to do. So what they do actually is try to do a very rough classification based on PSF shape, like a galaxy association and ascending trend, etc. I mean, but then even that, it gives you only rough classification. That means for supernova, you have a lot of supernova. Variable stars, you have a lot of variable stars. You don't know which one actually is of interest. So you have to, I mean, sometimes you have to pick one of them to do follow up and see what it is. I mean, you will miss a lot of things of interest. I mean, if you want to observe all of them, that's not possible because even the whole world actually lacks the spectral capacity to follow up all of them. And then that's LSST, the Large Synoptic Survey Telescope, and it has an aperture of 8.4 meter, and then even such large aperture, it still have a very amazingly large field of view of 10 square degree. But then, for a large telescope to have a large, field of view, I mean, the optical design, it actually introduced a lot of blocking. So like in this LSST case, so its real aperture is equivalent to, effective aperture is equivalent to 6.7 meter. And even with a 7 meter aperture, the detection limit is a 25 magnitude per exposure per scan. I mean, this is actually very amazing. I mean, but then, sometimes it just causes confusion problem. But anyway, this is, the machine, will be in operation soon. And the cost is very dearly, it's $750 million, dollars. That actually means, 4.8 billion renminbi yuan. Well, so that's the part. What is next? I think the next actually is trying to explore, very deep, and yet you want to have very short time scale cadence, right? But currently, when you go deeper than 20 magnitude, you found we actually lack the capability to catch the transients shorter than days. And it is hard to catch the early light curves for transients lasting months. They last months, but the early light curves of a few days is very hard to catch. But a lot of things like a supernova, like tidally disrupted events, like a gamma burst alpha glows, all like this. It's harder to catch their early light curves. And well, I mean, like we said when we talk about Zwicky Transient Factory, I mean, another difficulty actually lies in how to identify precisely the object of interest within hours. I mean, because you really need the first few hours to get their spectra, to arrange follow up. Well, I mean, most of them, they don't have the power because they lack the information, right? because within ours, they only have a few data points. So basically, I think the way out, the next step actually is we need to survey the whole sky at a cadence of hours, right? Well, but how? I mean, because if you want to use a single telescope with a large FOV, ZTF has already pushing the limit, and it has touched the ceiling. I mean, so, and still it cannot resolve the problem. So I think that the solution is not a single telescope. It must be an array of telescopes. So that's what our Sitian actually is doing. So the